So, hello everyone. This is Dr. Yuzo. This is EC318, Electronic Circuit 1, and I'm showing my Gantt chart screen here. Can everybody see it?
Yep.
All right. Thank you, Shane. All right, so let's move on. So we are at this cell. Obviously, homework 1 going to be due by the end of today, and also we gonna review midterm 1 by this coming Thursday, right? According to this Gantt chart. 1 week ahead of the midterm 1, so this coming Thursday is the lecture we're gonna review the midterm 1. Okay. We have, including today, 3 lectures to talk about the diode circuits. And the last lecture, if you recall, we have talked about the half wave and the full wave diode rectifier. And in the exam, I think I can have 1 or maybe 2 such kind of circuits for you to analyze. So today we gonna first of all go over 1 or more, 1 or maybe 2 circuits more, because the lab report require what? Requires this one, right? Requires this one and this one. All right, 2 and 5, 2 and 5. So today, I think last lecture we have done this one, right? We have done the figure 1. Am I right? Last lecture.
Yeah, I think so.
Yep. Yeah. So 2 and 5 left for you guys to analyze, and today let's have the circuit in figure 3 done. Okay, let's have this guy done. Let's see how we analyze the circuit over here. Figure 3. Okay. I'm repeating the figure 3 circuit in my notes like this. Right? The circuit over there about, and what we're seeing is a 1 AC source Vs, okay, whose waveform is given at like here. Okay, let's assume here as a peak value, a V peak, and obviously here is negative V peak, right? And also the zero crossing as 0 pi, 2 pi, and 3 pi, multiple times of the pi, right? And in the circuit, we have 2.2 kilo ohm and 2.2 kilo ohm here. So how to analyze the output? How to analyze this output? Anyone remember how we analyze such kind of circuit? Because we analyze the circuit and the behavior, and then eventually we can translate the behavior into the graph, right? Visualize the graph. So, anyone remember how we should start this? Where do we begin with? Anyone remember kind of a procedure? Can everyone see my
Analyze
screen?
with the diode being on.
Good, very good, very good. Shane is right. Shane is right. Kevin, can you see me now? No, not see me. Of course, you can't see me. But can you see my screen?
It still hasn't loaded. I've reloaded the page like times. I'll try again.
All right. Anyway, it's recorded, so you will be fine. Okay, you will be fine. Anyways, Shane is quite right. Okay, we kind of try to think where along this x-axis, which is the position in radians. Okay, it's not time t. Okay, be very careful. This is not time t. It's omega t. T is time. Omega t is not time anymore. It is position. Okay, so along the position x-axis, which time window is for the diode to be on, which is for diode to be off. Okay, this is something we need to at least roughly have an idea at the beginning, right? And then what do we do? Anyone recall? After knowing when is on, when is off, and then what we do? How to proceed? by checking your notes.
Don't you find what VO would be at that particular time?
Basically, yes.
Or
So basically,
the
if the diode is on and off, right? Two states, only two states for a diode, therefore only two states for the circuit, right? So with on state, what is the circuit? And then from that circuit, we go ahead to find V0. And for diode is off, that's the second state, right? So second circuit to find what is V0. Right? Respectively, the two states of the diode, and therefore only two states for the circuit, right? Two different circuits. Okay. So now let's go following Shane's idea. Let's begin with trying to identify which time window the diode is on, right? So in this circuit, what do you think? When the diode is going to be on? When? And why? Anyone can tell? When the diode is going to be on?
For now.
When the Vs is greater than the V gamma.
Vs is greater than the V gamma. Well, it's close, but not quite. We can think in this way, okay? When the voltage of Vs is too low, obviously, like Kevin said, it's not enough to turn on the diode because there's a V gamma, right? Cut-in voltage. So without exceeding it, you can't turn it on, right? So the diode is going to be off, right? However, let's say if Vs is beyond V gamma, is diode going to be on? Is it? From off becomes on? Is it? Not enough, right? Why is that? When it's off, here is open circuit, none. Only two same resistor in the circuit. And then you gradually increase the Vs, right? Increase the Vs, and what do you see? When it reach V gamma here, say here is V gamma. Is it going to be on? No. Why? Your Vs is V gamma, then what is the voltage across this 2.2 kilo ohm? What is the voltage there?
There has to be
When
enough
Vs
current to go through the diode, not just the resistor. Is that where I messed up?
No. We only talk about the voltage. So when Vs is equals to V gamma, what is the voltage across the diode then?
Wouldn't that just
Exactly.
be V gamma?
No, the diode is not on yet, remember. They're trying to turn on the diode from off. Okay. Does it make sense? Is it still
So
too
that
hard?
means so this is when the diode is off, correct? You're asking for the voltage?
Yes.
So if the diode is off, the voltage across that would be the voltage across the 2.2K resistor, so it'd be half of Vs.
Exactly, half Vs, which is equals to half V gamma, right? We just mentioned, we assuming Vs reached V gamma, then what is the diode receiving voltage? Is what? Half V gamma. Is not enough to turn it on. So when the diode is going to be turned on then? When the Vs reach what? What is it? Double V gamma. That's much better. That doesn't make sense? Because again, we are assuming before reaching the 2 V gamma, the diode is off, absolutely off, because the voltage is not enough. So obviously it's off, right? So you can, if not very clear still, then we can think in this way. Anyways, no matter what, you only have these two states, right? So when the diode is on, then what is the circuit? Right? This is the diode on circuit, which means we are applying what AC large signal model. The diode is equivalent to a voltage supply, V gamma, right? Then what if the diode is off? This is the resultant circuit, right? Does that make sense? So if we start to think from here, right? At the beginning, the Vs is small, so the diode is off. Then in this case, then the Vs increasing until somewhere the diode becomes on like this. However, what's the boundary? The boundary means the Vs must be equals to what? 2V gamma, right? You need to reach, in this circuit, you need to make the Vs, or say to make the voltage across the diode becomes V gamma. To make the voltage across the diode becomes V gamma, your Vs must be equals to 2V gamma. Does this make sense now?
Yep.
All right. How about Kevin?
Yep.
All right. So this is why good. That's why is actually we are looking for, or say we are waiting for the Vs to reach 2V gamma. Right? We're waiting for V gamma to reach Vs to reach 2V gamma, which is here. In other words, before that, this time window, the diode is off, absolutely off. Once you reach here, the diode is turned on. And then when it is going to be turned off, if you go on, when it's going to be off? Once again, V gamma, right? Once again, double V gamma, right? So here, the diode is going to be turned off. And before that, within this time window, the diode is on. Makes sense. So it's not exactly zero crossing, even though it's actually closed. Okay, it's closed. It's closed, but not very far away from the zero crossing here, pi, and here 0 is not very far. However, it's not exactly there. It's not exactly there. Okay. And then for the next on moments will be here. Sense? Yeah. Once again, it's not zero crossing here, but here. Here is what? This window is what? Off, right? This window is off. So now I basically finished one complete cycle. Okay. The rest of the position just to follow the previous cycle, right? So we know the diode on state circuit. We know the diode off state circuit. And then respectively, what is the V naught here and what is V naught here? And after knowing these two results, and then go back to here to plot them into the corresponding time window. Does it make sense? This is how we deal with the problem like this. Right. Any questions regarding this idea? All right, then what is the voltage output here? V naught equals what? What is
Would
it?
it be V gamma?
V gamma. V gamma. Very good. And then what is the output voltage here then?
Vs over 2.
Obviously, Vs over 2. This is the voltage divider in the circuit 1. Very good. Very good. The rest of the thing is how you translate these two results into the graph. Well, how about you guys try something? I can give you guys 3 to 4 minutes to try this out. Try this out. Go ahead. Just to translate these two results. Of course, if you have any questions regarding these two results, because you must understand, okay, must understand how you got there. Without understanding it, you're going to have trouble in the exam then. If these two results making perfect sense, then translate them into the graph. Let's talk about the solution here. So always keep in your mind that this result is corresponding to the diode is on. This result is corresponding to diode is off, respectively. Okay. So these results looks like what? If you when you translate it to the graph, what does it look like? This result.
It's just a straight line.
Exactly. It's a horizontal flat line, right? So what do you do? Very easy, right? Just whenever you see on, well, this window is on, right? This window is on. Okay. Straight line, V gamma. With value of V gamma. Constant. This is V gamma. This is done. And then next is V naught equals to half Vs. Half Vs is up to the Vs. Okay, it's up to the Vs, obviously up to the Vs. And then the diode, when diode is off, okay. First interval is here, a little bit tricky, but it's doable, right? So what do we do? The Vs is like this, shrinked by half. It's a little bit tricky to sketch. However, the beginning point is 0. 0. Who is the 0? Who is the half of 0? Remaining 0. Exactly. Remaining 0. This point remaining at 0. And the end of this interval is what? Here. 2 V gamma, right? So what is the half of the 2 V gamma?
V gamma.
Yeah, even my daughter can answer, right? So exactly, just like hook this two points up, basically. Try to give a curve that would be fair enough, right? And then this division is half Vs, okay. Vs is over here again. So you remember to label the peak, which is very much indicating right or wrong, right? The peak here is what? Half peak, of course, half peak. And then what do you need to do? Just connect. Does it make sense? Positive side up to V gamma, negative side up to half negative peak. Of course, here is negative. This is one cycle, up to 2 pi, up to 2 pi. No, it's more than 2 pi. Here is 2 pi big, because here is 2 pi, right? Here is pi. Does it make sense? Any questions?
Yeah, so for the exam, how many cycles do you just want us to do? Just one?
One should be actually more is enough. One cycle is actually fair enough. It's really fair enough. Okay. And of course, here to make it clear, I'm providing 1.5 cycle, trying to provide more insights. But one cycle is actually enough. Of course, by the way, what is the cycle of the output? What is the cycle of it? One cycle is fair enough, but obviously you need to know how long is one cycle, right? From 0 to what is one cycle? Anyone knows?
2 pi.
Exactly 2 pi. Okay, it's exactly 2 pi. You see, the beginning is 0. The ending is 0, which is 2 pi. This is one cycle. After 2 pi, it's pretty much repeating whatever here. Right? Pretty much repeating here. Here is 3 pi. Okay. Before reaching it, it's going to go down. Right? Repeating. So the cycle of the output remains as 2 pi, I guess 2 pi. Does everything make sense so far? Any questions? Yeah, 2 is right too. There's 0 to 2 pi. Yes, Daniel.
How would we do this for when we reverse the diodes? Same process?
Absolutely same. There's
Okay.
no difference at all.
It's just solving the circuits that would be different.
Solving a circuit, then what's the difference? Not a lot of difference either, actually, if you flip the diode.
Okay.
How about let's do this? Let me give you guys some 3 to 5 minutes. You guys do flip this diode. Do all of these all over. Give you 3 to 5 minutes, and you guys go ahead to reach as far as you could as an exercise. How about that? I can give you guys some time in the class to try it out, and I will present the solution. All right, go ahead. Go ahead. Oh, by the way, now since you guys all have the lab result, lab scope result, right? Compare your lab result with our theoretical result. You will see what? Same. If not, well, something wrong. Something wrong. Okay. Either your recorded lab result has something wrong, or you mess up the names, or mess up the orders, maybe, or what? Maybe Dr. Zhou should be fired, right?
Probably not.
No, I don't think so either. It's, I don't think I was kidding actually. However, you guys just cannot see my smile. So that's one of the bad things about online teaching and learning. Don't see the face. Once again should be perfectly fit whatever you received from the lab. Okay. Let's take care of the circuit with the diode flipped from here. If you flipped the diode, which part of the solution here we should modify? Let's begin with the diode is on. When the diode is on, then anything different here? The circuit.
You would flip the polarity of.
Okay, good, very good. We're gonna flip this. I'm using the red. It becomes this instead, and therefore the V naught equals what?
Negative V gamma.
V gamma.
Oh, very good. Negative V gamma. That's right. Exactly right. Good. Very good. Then keep moving. So when the diode is off, then what will we do here?
It's just the same thing, right?
Exactly, just the same thing. Very good. The V naught equals what? Of course. This is another question that my daughter can answer too. So V naught circuit remains. The V naught remains as well, right? All right. Then go back to here. Now is the key. Everybody listen up. You gotta correctly now understand or find out the time windows for the diodes on and off. This is different, quite different. Can you tell that? This is quite different. Okay. Therefore, let's say when the diode is on. when the diode is off, whichever easier for you. What we should say.
Diode would be
about-
on
Mhm.
at negative 2V gamma for
Negative
the
2V
VS.
gamma. Oh, very good. Kevin is right. Kevin is right. Negative 2V gamma. Okay, very good. He got it. Negative 2V gamma is here, intersecting with the VS at here at the negative half cycle. Perfect sense. Perfect sense. Does it make sense? It couldn't be positive cycle anymore. Positive half cycle, the voltage is applied like this. Your diode is flipped in this way, there's no way to be turned on. It has to be negative half cycle. Where is it? Your negative half cycle still need to overcome that 2V gamma. Therefore, it's over here. Negative 2V gamma is a very nice answer. Further intersecting with VS at here. So we're dividing the x-axis into. I'm sorry, this shouldn't be a pi. Okay, the pi is in the middle between blue and red. Okay. Here, the diode is on. Makes sense. Then before the on here, all the way to the 0, the diode is off. Does it make sense? Which means from here, go back to 0, and then this part off. Absolutely off. Right. And here is what? After here is also off. And to what? And to about here. Which is already beyond 3 pi. 3 pi is about here. Does it make sense? Then what does it look like? What does it look like? The curve, what does it look like? Let me use a green color. What does the waveform look like? When the diode is on, which is here, negative V gamma. Negative V gamma is here. Constant. Once again, constant. The value is negative V gamma. Okay, constant in this region. The rest of the place, what? Half V. Half VS, you need to go up to the VS. VS is over here, right? It's over here. What do you have? Like this, right? Label the peak value is what? Half peak. And to here, what do you have? Now the green is follow half VS, therefore is 0 crossing with 3 pi. Perfect sense. Perfect sense. Right? The first 0 crossing here is pi. Second 0 crossing here is 2 pi. Third one is 3 pi. Perfect sense. Is it to you?
Yep.
Everybody?
Yep.
All right, thank you, thank you. So this is the result. Well, look, compare it with 2 results. You see what they're what? Not only flipped over, they have what? Face off by pi. Right? So should your scope results from the labs.
So the waveform will always like be connected. So if you have it like broken up, that means you did something wrong.
Yes, that's true. That's true. That's a good point. Actually, good point. In other words, it's always should continuous. Yeah, there's no instantaneously changed waveform. No. So this is our figure 3. You know, one circuit. However, it's very complete. Oh well, of course we're not done yet, right? What's left? We still need one step.
The integral.
The integral for looking for the DC value. As I said, the exam it doesn't require that, but here let's try to write the to the red result. The red result, the DC is equal to average of this V naught, right? V naught, therefore is equals to what? We just mentioned was 2 pi, so integral over 2 pi. Integral over 2 pi, guess what? Not very easy because we don't know what is this radiant position angle, right? So we can roughly do this from 0 to pi, right? From 0 to pi is basically V gamma, right? Does it make sense? V omega t. From pi to 2 pi, what do we have? Half Vs, d omega dt. Does it make sense? So this is the VDC out of this. Let's go approximately, since we are not looking for an exact point here, because this shouldn't be 0. Here should be. But roughly, it's okay. Does it make sense? This equation?
Yep.
All right. And the green one equals what? Green one. V naught equals to also 2 pi as the cycle, and we have 0 to pi. What? Half Vs d omega t pi to 2 pi. What is it? Negative V gamma, right? Okay. Here we go. Here we go. And Vs, of course, we according to this, Vs, according to this, then Vs just equals to V peak sine omega t. Right? And then you substitute Vs here and here by this, and then go ahead to conduct the calculus. Any questions?
So in this particular case, this won't give us like a really an exact answer, but it'll just be like a rough estimate.
Yes, but shouldn't be off by too much. Shouldn't be off by too much. Well, I do have a question for you guys. Think about one question. How to increase the accuracy for these approximation? How to improve the accuracy for this approximation? In scenario, the accuracy could be improved. What can you do?
You would have to find the exact points in which
Absolutely,
diode.
absolutely, exactly. How to do that then specifically? How to do that? Exactly. The idea from Shane is find this moment. You find this exact moment right here and here, right? Because they are not 0 and pi. They're greater than 0, however, lower than pi, these two moments. Refine them. How? Anyone knows? Any idea?
You
By
would,
observing this, yeah, go ahead.
you would substitute V 2V gamma for Vs in that equation you've got right above the graph.
Oh, perfect. Here we go. One equation, one unknown. Looking for this unknown. Done. Because V peak is something specified. V gamma is something we know. Exactly right. Looking for this angle position, which is nothing but this point and this point. Very good. Very, very good. Very, very good. Great. Great answer. Great answer from Shay. Very good. Does it make sense, everybody? This is the equation. We really can do it. Okay, we can really do it. Does it make sense? But these points are what? They're nothing but the intersection point, the intersection position between the two V gamma and the Vs. Of course, you set this equation up. So this type of question is about what? Actually, I like them very much because this is assessing or say practicing the students' capability of what? Translation between visualized graphs and the mathematical equations. Okay. In electrical engineering, such capability is barely exercised. However, I think this is very useful. This is very useful. How you translate, how you link the waveform, to visualize the thing, and your mathematical, because your math is very dry, right? Students keep complaining, I don't like math, I don't like the algebra. Why? They're very dry, yes. Until you're able to visualize it. Actually, they're very colorful graphs, right? They're very colorful graphs. Okay, they're meaning something. They have real meaning. Okay. Until then, of course, you're feeling dry. However, they're not. Okay. All right. Any questions for this? For a very, very nice problem. Very nice problem and very nice discussions as well. Okay. If this fine, then we move on to our exercise. Okay, exercise. Let's talk about the basic diode circuits, which is more of applications. The diode, first the diode, specialized diode, of course. It's not the general p-n junction diode. It's not that one. It's specialized diode, very popular in our applications. The first one is photodiode. Photodiode. The photodiode is what? I think you guys have ever heard of this, right? A photodiode is what? Receiving what? Receiving light, which contains solar energy, right? And then it can generate what? Generate current. Right? So the light energy, the solar energy, is the photo current. So once again, if photo receiving the light and generate the current to conduct something, right? This is the photodiode. It could be made out of silicon, gallium arsenide, or other 3, 4, or 3 and 5 columns compound in the periodic table, right? And have been used to power many different electronics or battery charging. This is like what? This is nothing but like the solar panel, right? Solar panel. But solar diode is not exactly solar panel, but very close. And then, how do we explain such a phenomenon? There's some semiconductor physics theory behind. So you can understand the semiconductor in such way that there are different level of energy in the semiconductor. Okay. The higher level, of course, has higher energy. The lower level has lower energy. And higher level is called conduction band energy. And the lower level is called valence band energy. Okay, so to reach conduction band energy, you are going to be able to conduct. The semiconductor becomes pretty much conductor. Is generating the current flow through. If the energy is not enough, you drop down to the valence energy band, which is what? The conductor becomes the insulator, right? So between the conduction and valence band, there is a gap, energy gap, or say the difference, right? Which is called band gap, energy band gap, or forbidden band gap. This is the amount of the energy for the valence band energy jump over the gap to reach the conduction band energy, right? And this is the model of the energy behind it. It's physically existing, okay? It's not, it's just a model, sort of theory model. Right? So you can imagine the bigger the band gap is, the what? More energy is required for this semiconductor becomes conducting current, right? Okay. If from here jump over the gap to here requires how much energy? Okay, it's all up to how much the band gap is. Does that make sense? This is the model. This model, very popular energy model. Okay. So to us, that the key is once again the previous page, and just to remember that the photodiode means you're receiving the current and receiving the light and generating the current. Anyway, who is the opposite, behaving exactly opposite to photodiode? What is it? Opposite behavior is what?
LEDs.
Oh, very good. Excellent. Excellent answer from Kevin. Which is the next thing we're going to talk about. Nothing but LED. As Kevin just said, this time what do we do? We're not jumping up over the energy gap. We're dropping down. We just go down. Energy go down, and then I'm gonna go do what? Releasing energy in another format, which is light. The energy of the semiconductor is going down, jump down. Then you're gonna obviously releasing the energy to achieve that, right? So it's pretty much the current push the carrier jumping from the conduction band back to this band. It's releasing the energy in form of light. Okay, this is what LED does. It's what LED does. Okay, so once again, the size, or say how much the band gap is, matters. It matters. It means different level of energy you're able to release. Is this equation knock the door? Have you guys learned this equation before in physics class? What is it? Anyone knows? This equation here. Never heard of it?
I mean, I haven't taken physics 2 yet, but I haven't seen that one before.
Okay. All right, then worth a little bit of time to talk about it. And all right, so let's go back to our notes here. Just a little bit notes about this light energy. Light energy is equals to what? E. Represented by E. That equals what? constant H times F. So first of all, let's guess the easier one. Who is F? Who's
Frequency.
that? Frequency. Very good. Frequency of what? The light. Does light have a frequency? It does. Okay. What is the nature of the light? What's the nature of light? Wave, right? Wave. So it has frequency. However, it contains different frequency components. Okay. So different frequency, different light frequency, then give you different what? Anyone knows? Different light frequency give you different light what?
Energy?
Of course. But different light frequency means different light what? Anyone knows?
Is it color?
Wavelength and the color. Very good. Great. Okay, combine Shane and Kevin. Okay, very good. Therefore, what? Wavelengths and the color further determining how much energy you have. So guess what? In our sky, we have only white color, right? Am I right? There's no white color. Okay, there's no white color here. Right? The color we're seeing probably white. However, it's a mixing among what? Many different colors, many different visible colors, right? Many different visible colors. We will see what are those. And they have different colors, means what? They have different energy, okay? Different frequency, different wavelengths. Okay. This is the therefore, how to see the wavelengths? We can't see the color inside of the equation. However, frequency just equals to C over lambda. Who is lambda? Who is lambda? Wavelengths. Who is C then? But by the way, who is C and H? I don't know. What is C? Or any guessing?
I'm gonna say 2 pi.
The speed of light.
The speed of light. Here we go.
Yeah, I was way off.
That's all right. So then what is the value of velocity of light? What's the velocity of what's the value? It's a constant. C is a constant. What is it?
10 to the power of something with some number in front of it.
3? I don't know.
Something we can never catch, right? Anyways, something we can never catch. Okay, let me know if you could. Okay, so we both gonna quit here and become something like a superhero. Okay, and then what is the H then? Anyone know who is the H?
Wouldn't it just be a constant?
Yeah, constant. Yes. What constant?
Isn't it like Planck's constant?
Very good.
Oh, thought it looked familiar.
Is that the only one you're familiar with? So
Yep.
you guess that one?
Yep.
that you're right though. You're right though. It's Planck constant. It's Planck constant. And to be honest, I can't remember what's exactly the value is either. So this is a little bit light. Okay. The key is not any specified number. The key is what? The relationship between the frequency and the energy, and the wavelengths and the energy and the frequency. Does it make sense? The higher the frequency, the higher the what? Energy. However, the lower the what? Wavelength. Does it make sense? This is the thing you need to know. This is the thing you need to know. For what? Remember, in my exam, you have what? Anyone know what I'm talking about? In my exams, what do you have?
Formula sheet?
Well, that's the good part. I mean, what's the bad part? The students generally don't like multiple choice. Okay, multiple choice. So what kind of problem, what kind of knowledge is a good choice for the multiple choice? There we go. Does it make sense? Okay, so many students ask me how to prepare for the multiple choice. Well, unfortunately, the best way to prepare for the multiple choice is attending every day's lecture and engage in. Okay. Even though sometimes you can't remember everything, however, you have a little bit impression, and then review by the recorded lecture and the notes and the slides, and then you should be able to get there. Okay. Because even though multiple choice won't cover anything we never heard of, okay, that's not possible, not possible in my exams. Okay, it's definitely something we learned before, something we discussed before. Okay. All right, coming back to the slides. Here, the size of the band gap determines the wavelength. Of course, because the size of the band gap determines the energy. The energy determines further the wavelength, and wavelengths determine further the light color, like this. I'll ask you a question. Among this visible, all of these are visible colors, right? So among this color, tell me which color has the highest energy. Which color? Its
Would that
highest
be
energy.
purple?
Correct. Does it make sense? In other words, from the top to bottom, this way, energy is what? Dropping. Does that make sense? Okay. So this is the light LED, and further here, from here, you can see more details about the color and the wavelengths and the energy could generate. Okay, and specifically, what kind of semiconductor material, the compound, you can make that color for LED, right? And here, of course, the silicon-based material can only emit heat. It cannot generate light, color, light. No. Silicon cannot. Okay, so it must be certain compound. All right. Further here, the purple. Yes, the purple, it has the highest energy because of the lowest wavelength. Move on here. So we learned the LED, and before that we learned photodiode, and realizing that they both always appear in the same application for what? Signal transmission, right? So input signal here to be transmitted, it goes through what? Transmitter. Transmitter consists of what? The driver circuit, which is necessary in driving the LED, right? The LED is emitting the light. The light goes through the optical fiber and reach the receiver, so-called. And the receiver is whom? Nothing but photodiode. Photodiode receives this light from the optical fiber and generating electric current. The current to be amplified, the signal to be amplified, generate output, big enough output signal to be received. Right? So this is a typical application for this signal transmission. This is what? LED emitting light. Do you see the here? This is what? Receiving the light, generate the current flow through. So this is the photodiode, right? LED to diode. This is nothing but the input-output stage for signal transmission. Right? Does it make sense? Any questions? Right. If you don't have questions, I do then. So why? Well, you want to transmit a signal. Why you're bothering using transmitter and receiver? I just connect input and output. Well, you said you want to transmit this input signal to output end. Okay. I just hook up a wire. Right? Hook up a cable. Why bother using transmitter and receiver like this? Why bother? I mean, what is for? I have a wire. I have a cable. What is it for?
So if
Anyone
you
know?
want a different output than your input.
Different output or input. Well, I have more cable, more wires. Any thoughts?
Isolation for like
Excellent.
if
Kevin,
the input is, for like my instance at work, customer might be using 120-volt controls, but I use 24-volt DC controls. So we'd use that to isolate their stuff from ours.
You use that in your job, or?
Yeah.
All right, that's why. Now, Kevin has some experience. Okay, very good. The reason is isolation. Okay, a lot of scenario, your input and output at different voltage level, or say power level. Okay. Different power level, say input side is a control circuit with current rating like what? Up to 100 milliampere. Output end is what? Is maybe in power circuit, current up to maybe 10 to 20 ampere. But guess what? You can't directly hook them up. Okay, even though they're same signal, you can't directly hook up. It's too dangerous. The lower side circuit, control circuit, cannot take any high voltage, high current. Okay, so if you directly hook them up, it's very dangerous. Okay, you need to do isolation. Isolate two different power rating area, especially on what? PCB board. Okay, PCB. So isolation. Okay, isolation. Very good. Okay, so this is something must. It's not like we just figure out another way to transmit the signal. No, it's something must be done, okay, for safety.
Hey, Dr. Zoe, so why they use them in like for communication lines and stuff?
Communications?
Yeah.
Well, in that way, communications are using optical fibers, right?
Mm-hmm.
Transmission medium is a high efficiency and safer transmission medium.
Okay. Is it
Yeah,
more
power? I just present an example for power circuit, which makes more sense, right? In communication, as Connor said, is you don't have that much power consideration. However, you need to cover the long distance in between the receiver and the transmitter. In that way, the optimal fiber is a good material, good medium.
Interesting. Thanks.
Yeah, sure. All right, we can move on to see next. Well, here is I have ever used this optocoupler before for a driver circuit design, and so I give you example, specific example. This very model from this very Vishay Semiconductors is one of the semiconductor companies. They have different chips. Okay. Right. The third one we're learning is also a special type of the diode. Is Schottky Bayer diode. This is a common one. IV curve look like this. We learned before. Right? Common one. P-N junction diode. This is the so-called Schottky diode. What's the difference? According to the IV curve, what's the difference?
The cut-in voltage is smaller.
That's right. Cut-in voltage is different. Okay, not the shape, not the look. It's cut-in voltage, the nature is different. Cut-in voltage is smaller. Then the question is a good thing or a bad thing? It's better than the common p-n junction diode or worse than that, and why? Anyone knows?
It probably depends on the situation.
What kind of situation is gonna be good? What else gonna be bad?
If you're dealing with smaller voltages, you might want to use the Schottky, maybe.
If you're dealing with high voltage, then what do you want? Use p-n junction?
Yeah.
And first of all, if in low voltage application, why you prefer the Schottky?
If you had some sort of implication where you wouldn't get up to the cut-in voltage of say 0.7 volts or something of that sort, you would want to use the smaller diode, or the, you know what I mean?
Yeah, I do. What's the basically close? And the Shane's concern is basically close. But the more accurate explanation is like this. First of all, the smaller cut-in voltage is no matter what, no matter which application, it's always good. It's always good. Okay, it's absolutely superior to the p-n junction diode. How to explain this? What is the diode model in the say diode circuit? What is model? DC supply. Remember that? On model. Okay. Once again, this is an on model, right? Is this guy a good thing or a bad thing? It's bad. Why it is bad? It's a voltage drop through a switch. It's like a voltage drop through the switch in the on state. It's absolutely bad. Do you want to lose some voltage across something which is supposed to be ideally short circuit? Do you want to? Of course not, right? This is when the diode is on is like close to switch and the current can flow through. However, you're losing voltage across it, right? Because of this model, the voltage across it is always occupying some certain amount of voltage. It's bad. There's no reason to like it. Okay, remember this. There's no reason to like it. Okay, so we are losing some voltage. Remember that the half wave and the full wave diode rectifier, the DC output, always you need to what? Minus the V gamma. Okay? You always need to minus the V gamma. Why? Because the voltage drop. This is voltage drops through the diode. We don't like it. No reason to like it. Doesn't make sense. It's voltage drop. Why you want to lose the source voltage? No, we don't. Okay. So this is the reason why. We like smaller cutting voltage. The smaller the better. Okay. It's a voltage barrier. Okay. So you need to overcome it. Okay. So it's not something good. It's not something good. You're losing voltage on state. Okay? This is why. And then you have Zener. But this is one. It's one everybody knows what it is. Is utilizing the reversed biased breakdown voltage here. It's relatively small. What is the typical breakdown voltage for the Zener you ever used before? Anyone? Any experience? What is the breakdown voltage, generally speaking? To me, I ever used like a 3.3, 6, 9 volts. Okay, 3.3 volts perfectly for what? Protecting your control circuit, because the power supply sometimes, or say a lot of times, are 3.3 volt, right? If you have some experience related, you understand this better. But anyways, it's a very low breakdown voltage. Okay, remember this. This is the key. Very, very low breakdown voltage compared to the common p-in junction diode. Okay, because p-in junction diode, generally speaking, have very big breakdown voltage. You can hardly overcome it. Okay, that's why the IV curve for the p-in junction diode is like, it's go down here, right? Which means your breakdown voltage here is very high, reversely high, of course. However, the Zener has much smaller breakdown voltage here. So for circuit protection, once you have voltage beyond that, okay, it's conducting, it's shorted down to the ground, or okay, protecting the rest of the circuit. Okay. So again, Zener diode breakdown voltage reversely is small. Okay. All right. I think that's all for today. And as said, the Thursday we're going to review the midterm one, and also I'm going to teach some new diode circuits, the clipper and clampers. They're more difficult than the rectifier circuit. But following the similar logic and idea. Okay, we will see how to do the translation once again between the mathematical result and the graph, the waveform. Okay. Any questions?
Yeah, so for the lab report, what figures do you want us to do for the rectifier analysis?
Just say that again.
So for the lab report, what were the figures you want us to do for the rectifier analysis?
I think I have specified that in the announcement, right? Okay, did you guys receive the announcement here?
Yep.
Lab 4 report.
Okay, got it.
It's specified here.
Okay.
Once again, not only Josh, but everybody, okay? Be very careful to receive the announcement or any kind of a generalized information from the Canvas. You need to keep checking your email. You should be able to receive the email notification. Okay, make sure you are receiving those because it's very important. Speaking of that, I also post some very, very important information about the hands-on material because I saw some of you don't have enough hands-on experience, so I'm providing some extra supplemental materials. I hope you are not missing this as well. Not only this, I sent third very important information as well. Well, I received the comments here already from Noah. Is about NI multisym. Anyways, this is the end of the today's lecture, and if you haven't yet read through these 3 important announcements, please do so as soon as possible. All right. Okay, any other questions? All right, thank you for attending today's lecture, and talk to you guys on Thursday then. Bye now.